Hello everyone. In this video, I'm going to discuss an interesting problem. The problem is this. There is a grounded sphere and in front of the sphere, a point charge Q has been kept. So because of the presence of this charge Q, some charges will develop on this conducting grounded sphere. The question is, what is the ratio of charge induced on this portion, which is visible from the location of charge Q to this portion which is not visible from the location of charge Q. So that's the question. This question can be done in two ways, at least I think. One is using Gauss law by calculation of flux. So that is actually an easier method. And the other is by calculating density of the charges induced on the sphere. So we'll calculate density of the charges induced at some location, some arbitrary location, and then we will integrate the density on area to calculate the total charge induced on this portion and this portion. Okay, so I'm going to use here a second method. What you can do is if you want to try it yourself, you pause the video and you solve the question, and if you cannot solve, then look at the solution. And you can try by calculating flux also. Okay, that is, I think, is easier method. Okay, so let's do the calculation here by calculating charge density first. Okay, we'll calculate charge density and then we'll calculate the total charge induced. All right. So for that, we will be using image method. So we know that when a charge Q is placed in front of grounded conducting sphere, total charge induced is actually here. Q induced, if I write, this will be equal to minus Q into R by D. Okay. And if we use image method, then we will have to place an image here, which we will call Q dash. Okay. And let's say its distance from center of his sphere is X. Okay. So Q dash is actually equal to this charge. Okay. Value of Q dash comes out to be equal to this much. And location of Q, that means distance of Q from center of this sphere is actually R square by D. Okay. We want to calculate charge induced in this portion. Okay. And also charge induced in this portion, and then we'll calculate ratio of the two charges. Okay. So from here to here and from here to here, and we'll calculate ratio of these two charges. Okay. For that, what I'm going to do is I'll calculate potential at some arbitrary location. So let's see, suppose there is a point here. Okay. This is at distance R from center of his sphere. Its coordinate is R and theta. So I'm taking this angle as theta. All right. So this point is, let's say here potential is, let's say potential here is V R theta. Okay. And this point is at some distance from this charge, and it is at some distance from this image charge. Okay. So let's call it this distance as R1 and this distance as R2. Okay. So R1 and R2 we can calculate using cosine formula. Okay. See here, if we take this big triangle, okay, in this big triangle, this distance we are calling R and this distance is D. Okay. We can calculate R1. Okay. We have a triangle of this kind. You see here, we have this kind of a triangle. We have this distance as R, this is theta, and this is R1, and this distance is D. Okay. So R1 we can calculate. R1 will be equal to root under R square plus D square or minus 2R into D and cos theta. That's the R1. Okay. That's the value of R1. And similarly, if we calculate R2 in this small triangle, okay, there is a small triangle here. This side is X. Okay. So using the similar concept, you can calculate R2. So R2 will come out to be here. R2 is equal to, see, here triangle is something like this. There is a small side X, and this side is R, and this side is R1. Sorry, this is R2. This angle is theta. So we can calculate this X using cosine formula. This will come out to be R square plus X square minus 2X into R and cos theta. Okay. So that's the value of X. Okay. So using this R1 and R2, now let's calculate potential at this location, which we are calling V. Okay. And from potential, we will calculate electric field, and using electric field, then we will calculate charge density. So let us calculate potential first at this location. So potential will obviously be due to this Q and the due to Q primed. We we don't have a space here. So moving to other slide. So potential at location r and theta will be equal to potential due to q. So distance of given point r theta is r1 from q, so that is potential is kq by r1, and now potential due to q prime, so that is kq prime by r2. That is the potential. Okay. So let's put the value of r1, r2 here. See, r1 was equal to kq, and r1 was equal to root under r square plus d square minus 2r into d and cos theta. That is the value of this r1, and plus q dash. Q dash was equal to, sorry, r2. R2 was equal to r square plus x square minus 2r into x and cos theta. That's what I think it was. Okay. So now let's, to calculate electric field, we need to differentiate this one. So we are going to differentiate it with respect to r. Okay. There is a reason. Actually, we know that near the surface of conductor, electric field is equal to is actually equal to sigma by epsilon naught. Okay, and electric field near the surface of conductor is exactly perpendicular actually. So here, if you calculate electric field, okay, electric field will be exactly perpendicular in this direction. Okay, because this is negatively charged, so electric field will be towards the conductor. Okay, so since electric field is exactly perpendicular, that means it is in radial direction. So we only have to calculate radial component of electric field near the surface of conductor. Okay, so that's why near the surface of conductor we will put r equal to capital R, and we are calculating only radial component because there won't be any other component near the surface of conductor. Okay, so let's differentiate it with respect to r. So differentiation, see, I can take this denominator to the numerator actually. So its power is 1 by 2. So if you take it to numerator, its power will become minus 1 by 2. So if you differentiate it, you have kq, and here you will get minus 1 by 2. Okay, and this is r square plus d square, or minus 2 r d and cos theta. Its power will become minus 3 by 2. And when inside argument will be differentiated, this one, you will get here 2r minus 2d and cos theta. That's what you get. And when you differentiate this term again, you get here kq primed and r square plus x square minus 2r into x and cos theta. Its power is minus 3 by 2. And here, and also when you differentiate this one, you get a factor of minus 1 by 2. So that I had forgotten to write here. So let's write here. Now, when you differentiate inside the inside term, okay, you will get here 2r minus 2x and cos theta. This we are getting. Okay, 2x cos theta. So that this is the differentiation of v with respect to r. And we are going to put r equal to capital R everywhere. Okay, because we are calculating derivative near the surface of conductor so that we can get electric field near the surface of conductor. Okay. So let's put everywhere r equal to capital R, and we can cancel common terms. See, 2 will be common, so that can be cancelled with this 2, and there also 2 will get cancelled. Okay, so we'll get here kq and multiplied by, here you get capital R minus d and cos theta, and divided by, we can write this as capital R square plus d square minus 2 capital R d and cos theta, and whole power is 3 by 2. And here you get, there was a minus sign, so you get minus sign here. Okay, and here also there's minus sign. So here you get actually capital R minus x and cos theta, and there was a factor of kq primed here. And then we have here capital R square plus x square minus 2 capital R and x and cos theta. Whole power is 3 by 2. Okay. Now let's put the values of q primed and x. See, we have here q primed is equal to minus q into r by d. Okay. And x is actually equal to r square by d. These are standard results for image method that we apply for grounded conducting sphere. Okay. And it is also a well-known result that when you ground a sphere, we can just calculate potential and at center to prove that total charge induced will be actually equal to minus q by r, and image charge is also equal to that much. Okay. So these are the standard results that I'm using here. Okay. Now let's see. let's try to simplify it. So I'm going to put this here in place of x. So if I put, see, if I put that here, we will get, this term will remain the same. And here you will get r minus, in place of x, I'm going to put r square by d and cos theta. And in place of, this is k, and in place of q, you will put here minus q into r by d. And here we have, let's see, r square plus x square. X is actually r square by d. So this becomes r power 4 by d square, or minus 2r, and x is again r square by d and cos theta. That's what we have. Whole power is 3 by 2. So I want to make this denominator same as this one. Okay. So what I'll do is I'll take d square LCM, and I'll also take r square outside. Okay. So if I take r square outside, see here, this here we are going to get the same term, and here we'll take from this denominator d square LCM. So you will get here d square, and here you will get 1d. 1d gets multiplied here, and square will come in denominator. And when you take r square outside, so you are basically taking r square by d square outside this bracket. Okay. And whole power is 3 by 2. So 2 and 2 will cancel out. So that will become actually equal to r cube by d cube. Okay. So that d cube I'll take in the numerator. Okay. And you will get here r cube outside. Okay. So now you can take, see, 1 r will cancel out, and you can take 1 r also from here. You can take 1 r out. Okay. So basically r square will cancel out. And when you take here LCM, you will get here d minus r. Okay. And there is d and d, so d square will cancel out. Okay. So finally, I think we are going to something like this. After taking LCM here, you will get d minus here r and cos theta. Okay. And there is minus sign and this minus, so this will become plus. Okay. And here we will get k q or into d by r. Okay. Because from denominator, we are going to get this r cube by d cube. So one d cube will come in the numerator. Okay. That's what we are going to get. Okay. So finally, we will have something like this. And this denominator will become actually same as this one. Okay. Because see, when you take LCM, you get here d square, 1 r square will remain here. So d square plus r square, and 1d will come here, and r square we have taken, so 2rd. So here also we have 2rd. Basically, we are going to get same thing. So what I'll do is I'll write this as minus kq, and here r minus d and cos theta. Okay. Let's write a common denominator for both. Okay. So r square plus d square and minus 2r into d and cos theta. Whole power is 3 by 2. That's what we have now. Okay. So you see here, now if I take kq common and multiply by this d by r, okay, what shall we get? See here, this d, this r and r is going to cancel out. Okay. So let's take kq common. Okay. And multiply by this d by r. Okay. So kq I have taken common. Here when you multiply, you get here d square by r. Okay. And when this multiplies with this, you get here d r cancel out. So you get d cos theta. And from here, we have taken kq common. So there is minus sign. So you get here minus r. Here, there's minus sign and minus plus. So you get d cos theta. Okay. And divided by this, the same denominator that we have here. This one, d square plus r square minus 2 d into r and cos theta, whole power 3 by 2. Okay. Now you see here, this term and this term cancel out. Okay. We have this, we are left with this term. Okay. D square by r square minus this. Okay. So that is the dv by dr. Okay. So we have gotten dv by dr to be equal to, let's move to the other slide. So we have gotten dv by dr at r equal to capital R, that is equal to kq. And here we have d square by r and minus r. Okay. And divided by d square plus r square minus 2d into r and cos theta. whole power is 3 by 2. Okay, that's what we had. D square by R. Okay, and minus R. Okay, that's what we have actually. Okay. So that's the dV by dr. Now we know that near the surface of conductor, electric field is equal to sigma by epsilon naught. This is in radial direction. Okay. So we'll write here E is equal to, in place of electric field, we can write dV by dr at R equal to capital R. This is near the surface of conductor actually. So this is sigma upon epsilon naught. So therefore sigma is actually equal to minus epsilon naught and dV by dr. Okay, at R equal to capital R. That's what we have. So let's put that here. Okay, so when you multiply with minus sign, okay, you get here actually minus KQ and epsilon naught, and here you get D square by R minus R. Okay, and divided by D square plus R square minus 2dr at, sorry, d capital R or into cos theta. Whole power is p by 2. So that is the charge density induced on the surface of conductor at angle theta. At angle theta means this. See, at some location, suppose here, we have calculated here. So when we vary theta, we will get charge density at every point. Okay. So basically, we have calculated charge density at this location at angle theta. Okay. Now, let us integrate this charge density to obtain charge on the part which is visible from the location of Q. Okay, so we'll write, suppose this as Q1. Okay, so Q1 will be equal to simply sigma integrated over area ds. Okay, so we can write it as sigma. This is the charge induced. Okay, sigma and area is actually R square sine theta, d theta, and d phi. Okay, that's the area. So we are integrating over the area. All right, so we'll put this sigma here. So what we get here is constant term we'll take outside. So we will get here, see, there is R square. So when you multiply by R square, this will become, so we can write here like this, K Q epsilon naught and R square. Okay. And there is a term D square by R minus R. These things will come outside. Okay. And so we have this term, and we are left with here sine theta and d theta, and divided by d square plus r square minus 2 d into r and cos theta. Okay, power 3 by 2, and there is d phi term. Okay, so we have to do this integration. Okay, there is single integration here. Okay, or let's write it like this here, power 3 by 2 and d phi here. Okay. All right, so we have to do this integration. Okay, so I'm writing this Q1 is the charge induced on the part of the sphere which is visible from the location of charge Q. So let's see here. So what limit we should take actually. So here we have, see, this much portion. See, I have drawn tangent on the sphere from the location of Q. This is tangent on the sphere from location of Q. So only this part here up to here, this up to red line, this part is visible from the location of Q. So we are calculating charge induced on this part. Okay. You see here, this is tangent. So therefore the angle here is actually 90 degree. This angle is 90 degree. Okay. So in this triangle, I can calculate the value of theta. See, suppose this angle, suppose I call this angle as, I'm using a red line. See, this angle I'm calling alpha, suppose. Okay, so you can see this in this triangle, this angle is 90 degrees. So if you use cos alpha, this will be base, and this side will be hypotenuse. Okay, so if you use here cos alpha will be simply r by d. Okay, this b by h. Okay, cos alpha is equal to this much. Okay, and let's take this direction as z direction. Okay, so because theta we are measuring from this direction. See, the sphere is present all around z direction. Okay, so so therefore phi limit will be actually 2 pi. Okay, we can take phi limit to be 2 pi. Okay, so here if you put theta limit will be theta equal to 0 to some alpha, where cos alpha has been written as r by d, and phi limit will be 0 to 2 pi. So there is no phi term. So this phi will directly give 2 pi. Okay. And see here, k is actually 1 by 4 pi epsilon naught, that we all know. K is equal to 1 by 4 pi epsilon naught. So if we put 1 by 4 pi epsilon naught here, okay, epsilon naught will cancel out, and from 1 by 4 pi epsilon naught, this d phi will give you 2 pi. So only a factor of 1 by 2 will be left. Okay. So we are going to get something like this minus, if you take LCM here, you get d square minus r square. So 1r will cancel out. So you are going to get here q, and here you are going to get d square minus r square, and divided by 2, factor of 2 will come. Okay. That's what we get here. Okay. And this integration, okay, integration on theta will be left here. So let's write it as integration on theta is actually sine theta d theta, and divided by this factor d square, sorry, r square plus d square minus 2r into d and cos theta. This thing is left. Whole power is 3 by 2. Okay. And limit is 0 to alpha, and I have written here cos alpha. Cos alpha is equal to r by d. Okay. So let us integrate it. So to do this integration, what you can do is put cos theta is equal to t. Okay. So if you differentiate it, you get here sine theta d theta is equal to minus dt. So in place of sine theta d theta, we'll put minus dt. Okay. And when you put theta equal to 0 here, you will get t equal to 1. And when you put theta equal to alpha, you will get cos alpha. And cos alpha is equal to r. So this limit will become 1 to r by d. Okay. But there is a negative sign in dt. So to absorb that limit is negative sign, I'll reverse the limit. Okay. So we can take limit as r by d to 1. Okay. So this integration we are doing, okay. Suppose we are doing this integration. Later on, we'll put this here. Okay. So this integration we are calling this integration is I. Okay. So we'll get here dt, and here we get r square plus d square minus 2r into d. Okay. And cos theta is t. We have put cos theta equal to t here. So we get here power 3 by 2. All right. So now this integration is simple. Here we can do this integration. We'll get here r square plus d square minus 2r into d into t whole power. It will become minus 1 by 2 and divided by minus 1 by 2. Okay. And since coefficient of uh, t is minus 2rd, so we'll have to divide by minus 2rd. And here limit is r by d to 0. Sorry, to 1. Okay. So this 2 factor of 2 will cancel out. So you'll get here 1 by rd. And when you put here 1, okay, so it will become r square plus d square minus 2rd, which is d minus r whole square. So when you put whole square, it will become actually 1 by d minus r. Okay, that's what you will get. And when you put here this in place of t, you put r by d and d will cancel. It will become minus 2r square. So you subtract with this, it will become d square minus r square actually. So we can write it as 1 by root under d square minus r square. So that is the integration we got from here. Okay. So that is the integration, and we are going to put that integration here. Okay. So finally we are going to get q1 is equal to, so in here we are going to put, so we get minus q, and there is a factor of d square minus r square. Okay. And divided by 2. Now, the 1r we had cancelled here. So 1r was left actually. So there will be a factor of r also. There is a factor of r. Okay. So there is a factor of r. And now we are going to put this here. So 1 by rd. And here we have 1 by d minus r and minus 1 by root under d square minus r square. This we get. Okay. So now you can cancel this r and this r. You will be left with 2d in the denominator and multiply d square minus r square. Okay. So you will get here minus q upon 2d. And here, when you multiply by d square minus r square, we can write it as d minus r, d plus r. So d minus r will cancel out. You'll get here d plus r minus. And when you multiply this dr square minus r square with root factor, you will get a root factor here, d square minus r square. So that is the charge induced on the part which is visible from the location of given charge q. Okay. So this is the charge induced on the part of the sphere, which is basically on this part, as I mentioned earlier, on this part from here to here, on this whole part. This is the charge induced. Now we want to calculate charge induced on this part. So we know that total charge, which is minus q r by d. So we can just subtract charge induced on this part, okay, from this one. Okay, so to obtain charge induced on the part which is not visible. Okay, so let's call that charge as Q2. So Q2 will be equal to minus Q into R by D and minus Q1. So let's put the value minus Q R by D and minus Q1. See, Q1 is actually Q. Q1 is this is minus Q by D. So we'll get here Q plus Q by 2D. Okay, this is Q by 2D, and here we'll get here D plus R and minus root under D square minus R square. Okay, that's what we have, D square minus R square. Okay, so now let's subtract it and see what we get. So we can take here Q upon minus Q upon 2D common. Okay, so let us take this term Q upon 2D common, because in Q1 also we had this term common. Okay, so if you take Q minus Q upon 2D common here, you will get here, see, there is no factor of 2 here. So 2 gets multiplied here. So you will get plus 2 and 1 R is left here. Okay, because Q by D I have taken common. Okay, and here it will become minus. So this becomes actually minus D and minus R, and but this becomes plus root under D square minus R square. Okay, now you subtract 2R. So it will become D minus R. Okay, so we can write it as minus Q upon 2D. And here we are going to get this term is actually, here we had gotten minus D. So we can take minus sign common, and we get here D minus R and plus root under, that's what we have, right? D square minus R square. This we are getting. Okay, so this is the Q2. So Q2 we have this, and Q1 we had, Q1 was equal to minus Q upon 2D. Q1 was minus, right? See, this was minus Q upon D, and D plus R, we had this D plus R and minus root under D square minus R square. This is what Q1 was. Okay, so now we can divide the two. Okay, so we have to calculate Q1 divided by Q2. Okay, so when you divide the two, you will get here minus, these factor will cancel out. You will get here D plus R and minus root under D square minus R square, and here you get minus D minus R and plus root under D square minus R square. Okay, now you see here we can write this as D minus R and D plus R. Okay, so we'll get here Q1 divided by Q2 is equal to, this is D plus R, and this can be written as D minus R and D plus R. Okay, and here we have, this is D minus R and plus root under, this can be written as D minus R and D plus R. Okay, now you see here Q1 divided by Q2. If you take from here, if you take D plus R, root under D plus R common, this factor. So we are taking D plus R common. Okay, and from here we are taking this D minus R common, root under D minus R from denominator. So from numerator we are taking D plus R common. So we'll get here D plus R factor is there. So you'll get here D plus R, and plus here you will get here root under D minus R. Okay, and here if you take D minus R common, sorry, there was a negative sign in the denominator. Okay, in the numerator also there was a negative sign here. Okay, so there is a negative sign. So here there is a negative sign. Okay, so and here if you take D minus R common, you will get here minus root under D minus R, and here plus root under D minus R we have taken common, so we are left with D plus R. Now you see this term root under D plus R minus root under D minus R, same thing we have in numerator. So these two factors cancel out. So we actually get Q1 divided by Q2 is equal to root under D plus R and divided by D minus R. So that is the ratio of charge induced on the part which is visible from the location of Q to that which is not visible from the location of Q. So I have solved this question by directly calculating charge density induced on the surface of a sphere with the help of potential at some arbitrary point. This question can be done, as I said earlier, using flux method. So uh, I would urge you to try that method. Okay, you can calculate flux. Um, so I'm not giving you complete hint. Just I'm giving you an idea that using flux method also this question can be done. So do try it. And if you do not get the answer by flux method, then you can mention in comment box that you need solution by flux method also. If some students need a solution by flux method also, then I'll provide that solution. Okay, as well. Let's stop here now.